Welcome to another Code You Can Use screencast. Today we'll talk about reactive state management and implementing a generic reactive store with Project Reactor using TDD, test-driven development. So what is reactive state management? Reactive state management is most commonly used in component-based front-end application frameworks such as React, Angular, Flutter, Vue, SwiftUI, and so on. Some examples of this reactive state management libraries would include Redux, Flux, NGRX, and Block. Some of these names you might already be familiar with. So why use a reactive state management library? Reactive state management provides a few functionality that might be useful. It is a single centralized source of data, and it enforces a single directional data flow. The data is provided in a reactive data stream and is pushed to subscribers. And as such, the data is immutable and the state is modified through atomic atoms. This functionality are very useful in a component-based framework where you are managing data across many different components. Use cases for the server side would include things like sharing real-time application states, for example in team to-do lists, voting systems, team messaging systems, or having real-time data derived from external sources. For example, you might have an investment portfolio that's calculated from market data, route planning functionality that's based on weather and traffic information. In addition to just implementing the classes, we'll be using TDD to evolve the design and implementation. In the first few steps, we'll implement a CounterStorm class with initial value, a reactive data output, increment and decrement operations, and we'll also use atomic long for the counter value. And in the next steps, we'll replace the operations with counter action classes, the counter increment action and the counter decrement action. After that, we'll evolve the class further by replacing atomic long with atomic reference and the counter value object. We'll move the increment and decrement update functions into apply methods in the counter action classes. And we'll introduce a counter action interface as a superclass for the counter action classes. We'll then make both the actions and the store generic by replacing them with action parameterized by the counter class and store parameterized by the counter class again. So this might sound a bit mumbo jumbo, so let's dive right into the implementation to see how this is done. To begin with, let's start a Spring project in IntelliJ. We include the reactive web dependency to pull in the Project Reactor libraries. We'll implement Reactive Store for a counter value in a class called CounterStorm. And we'll go ahead to create the CounterStorm test class to drive the development. CounterStorm should be constructed with an initial counter value, so let's write this test case. In this test case, we create a CounterStorm instance with an initial value of 10. The subject of this test is the flux of the long values from CounterStorm. We'll now use the step verifier to verify that the initial counter value is in the value stream. Don't forget to use verify complete to ensure that step variable actually verifies. Now that the test is in place, we'll implement the simplest value stream that passes the test. We run the test and it works. Instead of a fixed initial value, let's now use a random long as the initial value. We extract this into a variable so that we can use it in the expected value. Running the test now, we see that the previous implementation is insufficient. So we want the value stream to be a flux reflecting the state of the counter store. We change that, and now the test passed. Next, we should be able to increment the counter store by a delta value. Since we will need to create the counter store with the random initial value and test subject again in each test, let's move these variables into the test class fields and initialize them in the setup method. Now we'll create the test again using step verifier, and we'll take the first two values from the values flux for the test. We expect their values to be initial and initial plus delta. Again, make sure that we end this with verify complete. Delta will also be a random value, and to get that, let's extract the generation of a random long into a method. We also need to tell CounterStore to increment by delta, and we do this by using the then operator on the step verifier to run a increment method on the CounterStore instance. Now we create the increment method in the CounterStore. In this method, we need to add delta to the state variable, which is straightforward, and then to emit the new state into the value stream. To do this, we need a sync. Let's go ahead and create a value sync field. Since value stream is a flux of long, the corresponding sync will be a sync of many of long values. We'll have multiple clients to CounterStore, so this is a multicast, and we'll use the default back pressure strategy for now. The output value stream will be a flux from this sync. We can now emit the new state into the value stream. And don't forget to emit the initial value of counter upon initialization of this class. And let's now go back to run the test again. Let's run all the previous tests to make sure that this works. We find that the test is getting stuck, and we need to go back and make sure that we are just taking the initial value instead of waiting for the entire value stream to complete. Now let's go ahead with decrement by delta. It's pretty much the same test, so we'll just copy and paste and create the decrement method, which is very similar to the increment method. Now let's go ahead and run the test. It passes, and let's run all the previous tests to make sure that everything is alright, and they are. So far we have only tested single increment or decrement by delta. Let's create a test to test both at the same time, and we would take 5 of the initial values, and we will decrement and increment this 4 times. So let's generate the random deltas for this. And we try to mix up the decrement and increment to make sure that we give the test some good workout. Okay, that should work. So let's run it and see, and it does work. Now let's run everything again, and everything still works. Our counter store should work correctly under concurrent access, so we need to change the long of the state to atomic long. And with that, we need to make a couple of changes to the methods, the increment and decrement methods, to use the atomic operations. So now coming back and running the test, and they still all pass. We now want to make the store more decoupled and generic, and to do that, we are going to change the operations to dispatching of events. So in this case, we have a dispatch of the increment action event. So let's do that, and we'll create a new counter increment action of delta. So we also create a new dispatch method in the counter store. And this would need to get the delta value from the action. Let's try running that, and it works. Okay, now let's move on to dispatching a decrement action. Again, it's pretty much the same test, except that we now have a decrement counter decrement action class. Let's create that. Okay, we find that the IDE has created this as a subclass of counter increment action. So we don't want that. We want it to be separated, and we implement the same value field in the decrement action. And now let's run the test, and it works. Okay, let's go on, and let's dispatch both increment and decrement actions to the same counter store. So again, let's copy from the previous test and change all these increment and decrement actions to operations to their corresponding dispatch actions. Okay, everything seems to be in order. Let's run the test, and it passes. And let's run everything again just to make sure we didn't mess up anything else. Okay, now we want to remove the direct cost to the increment and decrement operations, and just keep the dispatch of the actions. And now coming back to the counter store, we would replace and eliminate the direct operations, direct increment and decrement operations, and everything still works. Now we take another step to make the counter store more generic, and we want to do this by changing the atomic long to an atomic reference to a value class counter. Okay, so that means we need to make a number of changes to the methods. So counter is just a value class with a value field. And we also need to change the add and get to an to a function, which is an update and get with the corresponding addition and subtraction. Now let's do it for the counter decrement action. In this case, we want to create a new counter with the old value, with the value we get from the old counter, and then subtracting the delta from it. Okay, yeah, okay, that seems to be correct now. Now let's go back to the test, run everything again, and we find that something is not right. In this case, we need to get the value from the counter, and that's why we are doing a counter get value, okay, before we do the test. Now we want to push the update function into the action class itself. So we are going to use a apply method on action class, and now this should return we change it to make sure it works for counter increment action, and let's do this now for counter decrement action. It should work in the same way. Now let's go back and run all the tests, and they still work. Going back to the CounterStorm and looking at the dispatch methods, we find that both of these are very similar. So for the next step, we'll create a counter action, which will be a superclass of both the increment action and the decrement action. Let's create this as an interface, and let's make both the counter increment action and the counter decrement action implement this interface. So now we can simplify the implementation by using exactly the same implementation of the method for both the increment and decrement actions, and we can delete the dispatches from previously. Now let's run this, and everything still works. Let's now go further, and we try to change the counter action into a generic action class that takes a parameterized type T. So now we have to go back and fix both the implementation of dispatch as well as the implementation of counter increment action and counter decrement action. Now let's run the test, and it passes. We want to take the next step and make store a generic class that's parameterized with a type. In this case, counter as well. Okay, so let's replace all the counters with T. Okay, so that's and we also need to change the test. Let's just look through, make sure everything is okay. And now let's try to run the test, and it passes. Okay, so now we have both generic action and store. We can move this to a different package. We call that the Reactive Store. And the classes that are specific to counter, we can now move them to a sub package that's called counter. Let's run the test again, and it passes. That concludes the implementation of this counter store and the generic action and store classes that can be used as templates for your reactive state management library. So if you like this and find it useful, be sure to subscribe, and please let me know how you feel about this screencast in the comments below. Thank you.